Welcome back to Physics 141 Online. So far in our discussion of rotational motion, we've been describing the properties of a rotating object where the axis is fixed. So somehow the rotation axis is nailed down and can't move, although of course the object rotates around that axis. But now we'd like to look at more complicated kind of motion where not only can the object rotate, but it can also translate. So its center of mass can move as well as having rotation occur around an axis. And in this case, the simplest location for that axis would be through the center of mass. Now this can happen in a couple of different ways. One way that we can combine translational and rotational motion is to throw an object through the air, like a baseball. So the center of mass of the baseball is traveling with a certain velocity, and then if the baseball has spin on it, it's rotating about the center of mass as well. Another case, and this is the one that we're going to analyze more closely, is that of rolling motion, where the object that's rotating is in contact with a surface, and it's moving across the surface without sliding or skidding, so that the point on the object that is in contact with the surface instantaneously is not moving. Because of static friction, the point where the object is in contact with the surface is instantaneously at rest for just a moment until the object rotates a little bit further. And so this is a special case where we can write down a simple relationship between the velocity of the center of mass and the rotational velocity omega. We can show, if we consider when this object rotates through one complete revolution, we can see that the circumference through which it rotates would be 2 pi r. And the distance that the center of mass moves in a horizontal direction is also 2 pi r. And so we can see that the velocity of the center of mass is related to the rotational velocity omega through the simple relationship v center of mass is r omega. R, of course, is the radius of this rolling object, which could be a cylinder or a sphere, a hollow sphere, solid sphere, whatever. Lots of different shapes can roll. And this looks like a simple equation, but just remember that if this object is flying through the air, then there is no clear relationship between the center of mass velocity and the rotational velocity. The center of mass velocity could be large while the rotational velocity is small, or vice versa. But for rolling motion, this equation always holds. And what that allows us to do is write down the total kinetic energy for an object that's rolling as having a translational component and then a rotational component. I say component even though kinetic energy is not a vector, just to indicate that there are two parts to this energy. So the translational part is 1/2 m v center of mass squared, right? Because the whole object's mass is moving with a center of mass speed v. But then there's rotation about the axis through the center of mass, so we have 1/2 I omega squared, which you will remember is the expression for rotational kinetic energy. And of course the I that we use in this equation will depend on whether we have a solid cylinder, solid sphere, hollow sphere, so on. But we'll plug that in, but then in addition to that we can simplify this equation by putting in for omega from the above equation, omega equals v center of mass over r. And once we plug in the expression for the moment of inertia, then we can multiply this right-hand term out, and it will simplify significantly. It will look like, again, some kind of a fraction multiplying a mass times a velocity squared. And I'll do some examples in class where we show how this is applied. One example here that I'll just present and we'll work out in class is when you have a sphere of a certain mass and radius initially rolling with a certain center of mass speed that we'll call v0 on a horizontal surface, but then it's going to encounter a hill. And the question is, how far will its center of mass ascend? As it rolls up the hill and eventually stops before rolling back down, what's the maximum height that the center of mass will reach? And we can do this using energy conservation methods very similar to what we did a few chapters ago in the textbook, except now when we write down kinetic energy we have to account for both the translational and the rotational part. So that's a simple example. Another example that I will bring some props into class to illustrate is that of a downhill rolling situation. Let's imagine that we start different kinds of shapes at the top of an inclined plane and we release them all from rest and we ask in what order will they reach the bottom. And so we can have, as I mentioned before, we can have a solid or a hollow sphere, we can have a solid or a hollow cylinder, and those are shapes that will all roll easily. So if we release them all from rest, which one will get to the bottom first? And in what order will they reach the bottom? Qualitatively, we can really answer this question if we just compare the expressions for the moments of inertia about an axis that goes through the center of masses of these objects. And the table in the book shows us these relatively simple formulas that all have the form that they have some fraction times the mass times the square of the radius. And if we understand what moment of inertia really means, this table allows us to answer the question. Moment of inertia, sometimes called rotational inertia, remember, it measures the resistance of the object to being rotated. If you apply a particular torque to the object, an object with a large moment of inertia will resist being rotated more than an object with a small moment of inertia. And if you understand what that means, you should be able to use this table to predict which object will reach the bottom first. So think about that a little bit, and as you come to class, be prepared to make a prediction. Which one will be first, and then what the order will be, and then we'll see what happens. Of course, if we want to know something more detailed, like how fast is an object moving when it reaches the bottom, then we'll have to do something more quantitative, and we'll go back and use our equation for mechanical energy conservation. But there's a lot of qualitative insight that we can get just by looking at these simple formulas for the moment of inertia. So, hope this is a good introduction. I'll see you in class where I'll work out some more specific examples using these equations.